This video will take a look at the core applications of derivatives for our physics course. We will center our discussions based on a particular function, this x equals t cubed minus 1.4 t squared minus 4.8t, and we'll look to see what we can do based on the original function, and then we'll take the first derivative and see what sorts of things can be calculated from there, and then also the second derivative. So let's take a look at some of the types of things we can do. Here's a list of types of problems that could be asked. We won't look at every single one of them, but they are very closely related to each other. Our most basic problem is just to use the function as given to determine what an object's position is at a particular time. But don't overthink this question. This just means to plug in the value of time, in this case t equals 2. Everywhere you see t, making sure that you cube and square and so forth. And we want to keep in mind that if you have standard units in, you get standard units out. And so even though this looks very mathematical, it is still a physics question, and so you need to label your answer with units. So we can take this to the next step and talk about displacement. And recall that the word displacement means how far an object has come from its first position. So we are looking for the displacement between t equals 2 and 4 seconds. So we need to know where it was at 2 seconds and where it is at 4 seconds, and then just subtract those two positions. That will tell us the displacement, which is generally signified by a delta x. So basically what we did in the last problem, just twice. Okay, doing it for 4 and then also for 2 seconds. And again, that would come out to be a measurement of meters, 29.6 meters. All right, and the last thing that we do most of all with this sort of a function, just as it's given, is to determine the average velocity. Now, sometimes we can get a little fooled by that because it has the word velocity in it. So sometimes students will right away want to take the derivative and find the velocity function. But an average velocity doesn't depend on the particular value of velocity at a certain moment. For instance, if I wanted to find here the average velocity between 1 second and 3 seconds, all that matters is where was the object at 1 second, where was the object at 3 seconds, so I can figure out how far it traveled, and then how much time that took, 2 seconds. So what you're really doing is connecting these 2 points on the original function and finding the slope of that connecting line. All right, so our average velocity in this problem would be delta x over delta t, the displacement over the time. So we would find the position at each of those times and then divide by the amount of time it took, 2 seconds, 3 minus 1. And as we work our way to that, just kind of plugging our things in. Again, it's kind of nice when a problem involves 1 as our time. You don't need to worry about all the exponents and so forth. Simplifies our work. We end up with 2.6 meters per second. And the top of our fraction is a value of meters. The bottom is a value of seconds. All right, so let's see what we can do with the next step here. If we take this, this original function of position and we take the derivative, we find dx dt. There's a number of other things that we can find that actually relate to an object's instantaneous velocity. There's one thing listed here that we will not cover in this video, finding the maximum position of the object. That is a level 4 idea at this point in our class, and we're just going to focus on some of the earlier ideas in this video. All right, so one idea is to be able to find the velocity at a particular time, but I don't have an expression for velocity, I have an expression for position. Okay, so what I'm trying to do here is to look at that particular moment in time and to think about how sloped that curve is at that moment, which would be represented by this tangent line. So I'm really trying to find the slope of this tangent line. All right, well, that would be very complex to have to do if I had to do it by hand, but this is what our derivatives do for us. And so we would take the first derivative, dx dt, by multiplying the exponent times the coefficients and decreasing the exponents by 1. And then we would plug in the value of time. Okay, note that you can't plug the value in first, and then you just have a number. You don't have a function anymore. So always do the calculus step first. Another question that we may be asked to do is to find the average acceleration. Right, well, the average acceleration, again, is not you're not going to define that by looking at the actual acceleration function. The average acceleration would be how the velocity is changing with time. And so average velocity would be the change in v over the change in t. And so we would use this new equation that we have just found for velocity, and in that one plug in our 3 seconds and 1 second. And the difference between that would be our delta v. And then, just as we did in an earlier question, we divide by the change in time, which would be 3 minus 1, or 2. So here we get 9.2 meters per second squared. Again, standard units in, standard units out. Another really important way of using this velocity function is in a problem such as this, determining when the object stops momentarily. So when an object stops, it means its velocity is 0 at that moment. And so we will need to calculate that derivative, dx dt, and then set that expression, that function, equal to 0. So recall that our derivative ended up being 3t squared minus 2.8t minus 4.8. So that's what we would set equal to 0. That does force us to use the quadratic equation. If you have that in your calculator, you could just plug a, b, and c in from there. Or if you worked it by hand, it might look something like this. You'll get 2 answers, but in the very, very beginning of this question, we were told that this function only holds true for the object's motion between 0 and 10 seconds. Bring that slide back up here for a second here. So this is how the original problem was stated, that the function is only good between 0 and 10 seconds. So we would definitely need to throw away that negative value of time. Slide again here. Okay. So we'll just keep the 1.8 seconds. All right, so then the final thing that we need to be able to work with is if we take a second derivative and we determine an acceleration function from our velocity function. And so these are, again, various things that we might be asked to do with that function. And this one in red we will discuss a little bit later. So let's just look at a quick example here. This is just again, a core idea. If your acceleration is if your acceleration is needed at t equals 2.5, you would need to know what dv dt is, okay, which means you would first need to know what v is. So this is why I'm using the phrase second derivative, because we differentiate once and then we differentiate again. And that would give us now an expression for the acceleration, 6t minus 2.8, and at the value of t equals 2.5 seconds. Again, just plug that value into this new expression. All right, this video talks about just a few more applications of derivatives for our class. We focus mainly on situations where additional formulas need to be used, beyond just our basic motion ideas. So in this series, we will take a look at a car of mass 700 kilograms, and its position function is given as shown here. All right, so again, the mass doesn't really matter for this problem. Finding the car's velocity, we would take the first derivative, dx dt, and just follow our rules for exponent times coefficient and lowering the exponent by 1, and then plug in our value of time to find that this car travels at 21.38 meters per second, about 21 meters per second. Okay, if the question was worded this way, how far does the car travel within this time interval? Okay, it doesn't use the word displacement, but that's what this problem is asking for. What is the delta x? So we need to recognize that. Delta x would be the position at 2.5 seconds and then the position at 1 second. Find those two values and subtract to figure out where the object is compared to its position at t equals 1. So we get about 34 meters. Again, notice how we're putting standard units in, so we get standard units out. All right, the car's average velocity. Again, this is one that we talked about in the last video, but an average velocity is not related to the velocity at a particular moment. It's instead related to how far the object has traveled. So we found just a few seconds ago that this object moved 34 meters, and it did that between t equals 1 to t equals 2.5 seconds. Okay, so that's kind of the idea that we're going to be using here. The average velocity would be delta x over delta t. And so we could use that delta x from before. We'll use the more accurate version, not the rounded version in this step. And then our delta t would be 1.5 seconds. That's how long this movement required. So about 23 meters per second over the course of that time interval. All right, so let's involve another formula and see what we would do here. So this question asks for the net force on the car at a particular time. Hopefully you recall that net force is equal to m times a, F equals ma. And so what we need is the acceleration of this car. All right, so that recalls taking the derivative twice. The first derivative would find for us the velocity function, and then if we take the derivative of that, that will find us our acceleration function. So this comes out to be a constant number of 2.6 meters per second squared, so it really doesn't matter what time we are talking about. This object has a constant acceleration, therefore it has a constant force. And we can find that value of force by just multiplying the acceleration times the mass, 1,820 newtons. All right, something else that would relate to these sorts of values, we might be asked to find the kinetic energy of an object. And again, of course, we'd have to recall that kinetic energy is 1/2 mv squared. So what we need is a value of speed or velocity in order to answer the question. So that involves just the first derivative of this function. So the 2.6t plus 18. We put in our value of time to find the v for that particular moment, 26.32. And then we would involve the kinetic energy formula using the mass and so forth. So pretty high value, but this is a very large car, or a fairly large car, so 2.4 times 10 to the 5th joules.